In this lesson, we're going to look at maximum and minimums as well as end behavior. So when we talk about maximum and minimums, sometimes these are also called extrema because we're looking for those extreme values. So maximum would be the extreme height or the tallest that your graph can go on the y-axis, the highest point. And then your minimum would be the lowest point. Okay, so we're looking for those extremes. Now, your focus of your graph, the region you're looking at, is important. If you're looking at the entire graph or the entire function, that's known as the absolute maximum or the absolute minimum, meaning there aren't any points that are higher or lower. Okay, so this is for the entire function, the entire graph. And then relative would be just for a localized area. Okay, so relative would tell me that if my graph looks like this, okay, I have some localized maximums, right? Because it's lower on either side of those points. But then I also have some localized or relative minimums because it's higher on either side. So if I look at this area and this area, they are lower than a relative max. Okay, but then if I look at, let's see, if I look at this region and this region, those are higher than this relative minimum. Okay, so we have an absolute maximum or an absolute minimum, which is the entire graph, take the entire function in consideration, and then a relative max or min means just in a small area. So points on either side of it are going to be either higher or lower, making it a relative max or min. Okay, and again, we're going to look at our family functions, our parent functions, for some examples to see how to write out our solutions, and then your CYUs will give you a chance to practice this before you go on to your lesson check. Okay, so linear function y equals x. Please know you should be able to graph these without Desmos. The linear functions are the easiest ones to plot. So here, if you're going to put it in slope-intercept form, your b, so that would be y equals mx plus b. And the only thing we have in this equation is b, so that tells, or is x, sorry. So that tells me my slope-intercept is 0, so I'm going to cross the y-axis at 0. And then my slope is a 1, so I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, and that will create my line. Okay, now again, I'm going to make a note. This function goes on forever. I am not giving any restrictions as far as my x values. So this function goes on for to negative infinity and positive infinity. Okay, which means no matter what point I pick, I'm always going to find a higher point. Okay, so there is no absolute maximum. Okay, you could put none. And then also on the same token, there's no relative maximum, right? Because there's no place where we have a curve. So linear functions are straight with no restrictions. We have no relative maximum. Okay, and then same if we go down, if we follow the graph to the left towards negative infinity, it continues to get lower and lower and lower. So again, there are no relative extrema for a linear function if you don't have any restrictions on your domain. Okay, all right, the quadratic function, remember this is my parabola, this is the parent function, so I'll give you some examples in the CYUs where it's moved around on the graph a little bit. Okay, again, if we are looking for maximums, okay, we're looking for the highest point on the graph where the function doesn't go any further, and we don't have that. Okay, it's going to continue up to infinity, which means we also don't have any relative maximums. Okay, we have a continuous curve, so go to the left and the right, it continues to increase, it continues to go up. Absolute minimum. Now this we do have, because if you notice here at this point, the graph gets as low as it's going to get, touches the y-axis, and then starts to go back up. So we do have an absolute minimum. Okay, and remember, these are your y values because we're talking how high or how low our graph goes. So the absolute minimum would be at y equals 0. And we wouldn't necessarily have to list both of them. It's really just kind of an absolute minimum. But there are some textbooks that are also going to call this a relative minimum because it does qualify based on the definition. Okay, no maximums because the graph continues to positive infinity on both sides of your parabola. Okay, minimum means this is the lowest point. Okay, last one is cubic function, and I'm going to draw my arrows in to remind myself I go on to infinity. And because it goes up to infinity, we do not have any maximums, and there's no, for this one, there's no curves, right? Like I showed you in the demo. So we don't have any maximums. And again, as we work down, it just keeps getting lower and lower and lower. So we don't have any minimums either. Okay, now the cubic function is a function that can have this roller coaster look to it. So you want to make sure that you're looking at your graph carefully, that you're looking for those points where the points on either side are either higher than that point or lower than that point. Okay, next thing we're going to look at is end behavior. And this is one of the reasons that I wanted you to mark those arrows at the end of your graph, because that's what we're going to look at when we talk about end behavior of a graph. Okay. We are looking on the x-axis, okay, and we are trying to see what our graph is doing. So as x approaches, okay, so for the first one, we're looking at as x approaches infinity. So my x-axis is here. So we're going to follow the graph and see what is it doing as I move toward the right, towards positive infinity on my graph, okay? As I move on the x-axis to the right, my graph is heading upwards, so it's heading towards positive infinity. Okay, so we would read this as x approaches infinity, so this arrow means approaches, okay? F of x approaches, and then whatever your value is. So in this case, as we move to the right, our graph is going up and up and up. So we're going to say it approaches a positive infinity. And then the other scenario we have to look at is as x approaches negative infinity. So now we have to look at it going the other direction. So as we follow our function to the left, the graph is going down, down, down. So it's approaching negative infinity. Okay. We're looking at the ends of the graph. Okay, quadratic function. I'm going to put my arrows down here. Okay, as x approaches positive infinity. So again, we're going to look at the graph as I move this direction. Whoops, it didn't change color. Sorry about that. As I move to the right on the x-axis, what is my graph doing? Well, it's heading up. Okay, so as x approaches positive infinity, f of x, or my function, is also approaching positive infinity. Okay, and then as x approaches negative infinity, so as I move the left, as I go to the left, my graph is also approaching positive infinity. So it's going up on both sides, both directions, to the left and to the right. Okay, and then my cubic function, hopefully you're getting the hang of this, as x approaches positive infinity, so as we move to the right, my graph is going up, so it's approaching positive infinity. And then as I move to the left, my graph is approaching negative infinity. Now, these are not the only answers, okay? So you can have graphs that are approaching a specific value. If you have any questions, make sure that you let me know, and I'll see you next time.